everyone. Thank you for your time today. We'll get started in just a few moments, but in the meantime, I'm curious to know, how are you collecting geospatial information? A, airborne laser scanning, or ALS. B, unmanned laser scanning, ULS. C, UAV photogrammetry. D, both ALS and ULS. Or E, terrestrial or mobile laser scanners. And we have a good distribution here between airborne laser scanning, ground-based laser scanning, and a few in between. So thank you for providing your feedback. And this leads us into today's webinar topic, ULS versus ALS, a data quality case study. Now, before we start, please note at the bottom of your screen that there's a question box. Please feel free to add in your questions during the session, and we will do our very best to answer them at the end. My name is My-Linh Truong, the Unmanned Laser Scanning and UAS Business Segment Manager for RIEGL USA. Today, it is my pleasure to introduce Mr. Matt Thomas, the Geospatial Technology Manager for SAM LLC. He has 13 years of experience in the surveying and mapping industry, where his areas of expertise include UAS, mobile and fixed wing aerial mapping system development, geospatial remote sensing project approach development, geospatial data calibration and processing, conventional survey data processing, and conventional survey field data collection. Holding a Bachelor of Science degrees from Purdue University in land surveying and geomatics engineering, as well as civil engineering, he is a professional licensed surveyor in the state of Indiana, as well as a registered professional land surveyor in the state of Texas. Please help me welcome Matt.
Thank you very much, My-Linh. I appreciate the wonderful introduction. Thank you, everybody, for taking time out of your day today to join us for the webinar. And thank you, RIEGL USA, for the platform here to display this case study. At SAM, we serve our clients as consultants and trusted advisors. And as good consultants, we develop technical project approaches that help find a balance between schedule, budget, and quality. So in other words, producing high quality deliverables on time at an acceptable budget, that three-legged project management stool that we always talk about. And doing this at an acceptable budget to both client and consultant makes for a good, healthy client-consultant relationship. The majority of our clients at SAM are engineers who are seeking design-grade deliverables. Very rarely are we delivering just purely a point cloud, okay? In many cases, it is more typically a topographic survey or a real-world model of either the ground or of transmission structures for electric transmission work or distribution poles. And that becomes a combination deliverable, comprehensive deliverable of traditional survey, boots on the ground survey, and remote sensing data. And so for design grade survey projects, you know, as I said, the backbone of those projects and the good technical project pros has to be survey control, okay? And then we move into the remote sensing sensor and platform that we will then select, you know, and we look at the abilities of the sensor, the platform, the workflows that go along with each sensor and platform, and look at it from a quality standpoint of, you know, can that sensor and platform combined, you know, produce a data set that can then support a design grade engineering project. And over time, and you know, as trusted advisors and good consultants to our clients, over time in a long education process, you know, we've proven through that education process and through our experience and successful projects that ALS systems, you know, can knock it out of the park, so to speak, in producing that design grade data. And some of the attributes associated with those ALS systems that you know we've accentuated in the education process, you know, powerful lasers, high pulse repetition rates, high-end pause systems, million-dollar price tags on these systems in some cases. That allows us and our clients to kind of gain a comfort level with a remote sensing system that we can, you know, put on the project, go out there and efficiently acquire data to support their design grade engineering project. So enter ULS systems here in the last 3 to 4 years. They've become more and more prevalent, and the characteristics associated with these ULS systems in many cases are lower powered sensors, lower end POS systems, and 10% of the cost up front of that ALS system. So the question becomes, how can these systems stack up from a quality standpoint against an ALS system? And that's what we're trying to answer here with this case study today. Because if a ULS system can stack up from a quality standpoint, that gives us as consultants a ton of flexibility in our project design. We can now take a look at the most efficient platform or the most efficient sensor from both a schedule and a budget standpoint to roll out on this project. Okay, and it frees us up to go get other projects at the same time with the ALS system or the ULS system, not kind of be a one-trick pony, so to speak. So that allows us, again, to develop a technical project approach to be good consultants for our clients. So we'll take a deeper dive now into the case study. This particular site was a 73-acre design survey. It was a nice site for a case study because it featured multiple land cover types, hard surfaces, roadways, soft surfaces, heavily treed areas, had some distribution lines, some transmission lines in it, all of which we're going to show how we've reached data equivalency from a quality standpoint with these two systems. So the two systems that went head-to-head today are for this particular case study were the ALS system, the RIEGL VQ1560 Mark II, mounted in our Cessna Caravan, flowing at about 140 knots or 2,700 feet AGL over the site. It's a proven sensor and a proven aircraft, all matched up against the RIEGL Minivux 1 UAV, which mounted on it was an Altus Warp 3. And then, of course, a camera. All of our systems at SAM have dual sensors on it, always a camera, always a LIDAR sensor, so we have mirrored systems. In the case of the ULS system, 14 knots over the site and 260 feet AGL at that point. Flight time for the Orcs, it's 20 minutes. That's as long as it can stay in the aloft. The ALS system, of course, can stay up there for 5 hours. So the ALS guys in the crowd are sitting here going, how in the world could the ULS system really stack up against that level of efficiency and the capabilities? And they've got a point. But let's we'll work through the case study here and see how it stacks up. So a good place to start when we're evaluating from a data quality standpoint is, to me, the sensor spec sheet. And we're all familiar. I assume most of us are familiar with these sensor spec sheets. Something that first jumps out at me on this is when I look at the ULS spec sheet, in the screen capture here, we've got a majority of the spec sheet in the actual screen capture. From the ALS standpoint, we've got only a small percentage of the spec sheet. That ALS system is it's a way more capable system. But what I really want to drive down into is what I've boxed here. It's the accuracy and precision of the two lasers associated with each one of these systems. Because at the end of the day, we can't be any more accurate than the laser device that we're using to measure what we're trying to measure. So the ground in this case. Okay, so we really can't drill any tighter in this case from an ALS standpoint than 20 millimeters, or from a ULS standpoint 15 to 10 meters. They have an equivalency off the bat from a range accuracy perspective. So that tells me with good workflows, okay, and assuming we can acquire good solid ground data with both systems, we should be able to process these down and get equivalent data sets. So with that, we'll jump into the acquisition plans for each of these systems. The ALS acquisition plan, of course, was 3 lines over this 73-acre site. A whopping 10 minutes in the air, assuming that the pilot was taking an easy day and making slow turns. It was actually probably quicker in practice. But anyways, 10 minutes over the site to get the job done. The MOB and demob to the site in the $1 million aircraft with the $1 million sensor took longer, and the static session sitting on the tarmac before and after took longer than it did to actually collect the site. So again, the ALS folks in the crowd are going, how is this not the best approach from an efficiency standpoint? But something that we're not taking into consideration from a true collection standpoint, or something we have to take into consideration, is that we still needed to send a survey crew to this site. As I said earlier, survey, boots on the ground survey, has to serve as the backbone of a good technical project approach development for a design grade survey. So with that, that survey crew needed to set control for us to calibrate the data set down to and remove biases, systematic and random and whatnot within the remote sensing data. LIDAR isn't magic. It does struggle with vegetation penetration in very thick, low vegetation environments. So we need boots on the ground survey to kind of fill in some of those gaps and some of those holes within our survey. Again, producing that comprehensive final deliverable, not delivering a point cloud, but delivering a true design grade survey in this case. We also need survey crews out there to shoot in drainage structures, pipe inverts. Those are all critical features that go into this engineering design grade survey that we're delivering. So in this case, we're mobilizing 2 crews to the site, 1 in the airplane, 1 in the survey crew, okay? So we'll move on to the ULS acquisition plan. And the first thing that jumps out at me when I look at this ULS acquisition plan is the massive amount of flight lines that we have on the site. And this works out to actually about 7 total missions, 7 20 to 25 minute missions, or about 4 hours of flight time. So on the ALS side of thing, we were 10 minutes over the site. ULS side, we're 4 hours over the site. There's clearly a bias there from an ALS standpoint of how efficiently we're getting this site collected. But here's where the ULS starts to catch up a little bit. That same survey crew that mobilized to the site to set that survey control, set a base station potentially, topo in possible obscured areas and drainage structures, they also happen to have that ORC and that LIDAR sensor mounted to that ORC in the back of the truck. They also served as that flight crew. So now in their daily job of topoing the site and providing that survey backbone, they're also doing the UAS or doing the remote sensing acquisition. Okay, so we're mobilizing now 1 crew with a lower cost aircraft and a lower cost sensor to the site. So from a schedule and a budget standpoint, we're starting to draw even on a site of this nature with the ULS system, when we compare the ULS to the ALS system at that point. So, but none of that matters from a schedule and budget standpoint if we can't produce a quality data set on the back end with the ULS system like we can produce with the ALS system. So that's where we'll get into the meat of this. So our first evaluation after the initial acquisition was completed for both systems was how we do from a point density standpoint. Reviewing our laser spec sheet, we saw that when we shoot both of those lasers at the ground, as long as we hit that ground and get good returns off of that ground, they're going to have a similar range and precision, range accuracy and precision. So that's a positive, but did we get to the ground? Did we get there? And so that's what did we get the number of returns that we need? So that's what we're looking at here in these density rasters. The red polygon that you see are the western extents of the project. We're kind of focus on this area because it has the land cover types that we need. It's a nice area to focus on within the site itself. Anything in red in this raster is less than 20 points per square meter over the project area. Anything in yellow or other, okay, any other color at that point is greater than 20 points per square meter. So the positives that we see here when we compare this ULS density raster versus the ALS density raster is that we actually achieved a higher point density with the ULS. We did have a lot more flight lines out there, but we got a good amount of returns in through these forested areas as well, and these vegetated areas. So there's not a lack of returns, at least from the density raster in a high level view. We'll dig down into some of these different land cover types here in a bit as we get a little bit lower. So after checking the box on our point densities, our next evaluation becomes how do we fit to the real world from an absolute accuracy standpoint at control. And to get to these calibrated point clouds, we handed the ALS data set and the survey control off to one calibration technician, ULS data set and control off to a separate calibration technician, gave them the same instructions on the quality from a flight line to flight line calibration standpoint, that we needed returned and the quality of data set to control standpoint that we needed returned, and collected their calibrated point clouds after the fact and their calibration reports. And what jumps out to me in these calibration reports is we achieved a very, very almost scary similar result in our overall RMSEs, or how our ALS unified data set and our ULS unified data set is fitting to our final control from a vertical standpoint. You know, both were right at that 800ths mark at a 95% confidence interval at survey control. And so you don't think I'm cooking the books on this. You can look here at the individual deltas within this screen capture, and you can see they do vary. In 0.1 especially, in the ULS data set, it was off 600ths, and the ALS data set, it was off 8,000ths. Either way, though, we're driving a data set down to real-world backbone survey control that will meet an engineering design grade deliverable quality data set for both systems out of the box. And the other thing that's interesting to me too is this the vertical accuracies that we're achieving at the control are very similar to that range accuracy or that range precision cited back in that spec sheet. That tells me we're properly modeling out, you know, the systematic biases and whatnot through our process. And to kind of further illustrate how we fit control here, there's going to be a series of screen captures where red dots that you see in the screen captures are the ALS data, yellow dots are the ULS data. Again, they were calibrated independent of each other. They were not calibrated together. The only thing that brought them together would be survey control in this case. And so in this, you see the nice tight grouping of the two data sets together. And the circle in the middle is the representative of the actual survey control point. You can see how they're fitting real close to the center of that particular control point. So we know we're confident that we're good at control. And, you know, looking back at how we design the flight and plan the flights, we look at the ALS acquisition, and it was 3 flight lines at that point. So it was a nice consistent collection with a high-grade pause solution. We should have a very consistent flight line solution, not a lot of noise going on, not a lot of GPS error associated with it. That is our standard at that point. Okay, once that fits to control, we should be good in between control because of that high-end pause solution. Okay, so our assumption looking at our ALS or our ULS flight plan with all of the different missions, all of the different flight lines, there could be potentially a lot more error in between those missions and between those flight lines and a lower grade pause system at that point. So how does the next assessment we need to make on our ULS data, unified data set, is how does that ULS data fit or match to our ALS data in between control? And so we've made that comparison here utilizing what I call a DZ raster at this point. We took the unified ALS data set, unified ULS data set, laid them on top of each other, and had it calculate a delta between the two, looking only at the ground data in this case. So anything that is shaded in green here has a delta of 0 feet to 0.15 feet. Any bits in yellow here are 0.15 feet to 0.33 feet. And you can see circled in pink here are some of my ground control points scattered across the side on the western edge of the project here. And so you'll see we have a nice, beautiful green fields here. So we have good alignment between the two data sets from a relative standpoint and an absolute standpoint. Again, driving towards that equivalency of quality and our abilities to get there. But how does it look when we actually drill down to the data? Because the data is what we're going to be doing our mapping on. So let's look at some land cover types now and some different features within the point cloud to take a look at that. A natural place to start, of course, is with hard surfaces. Hard surfaces are always critical engineering tie-in points for engineers when they're designing a project. They've got to tie into that existing grade, that existing roadway. So our remote sensing data and the topo and the design grade surface created has to be representative of that existing grade, it has to be equivalent. So within that, we've got our ALS data again here in our red cross section, our ULS data in our yellow cross section. These are 1 foot. This is a 1 foot cross section across our roadway here. And in the middle, we have the nice unified point cloud mixing, a unified combination of the two cross sections there. Again, independently calibrated, but then just displayed here together. And we can see how we've achieved equivalent results from both systems on a roadway, in this case, or a hard surface. The next land cover type that we'll dig into, the sporadic trees / low vegetation area. Both sensors have multiple return capabilities. Of course, our ALS system is much higher powered system. But in both cases, we penetrated through this vegetation, and you can see a nice grouping of the ALS and the ULS data on the soft surface underneath these trees. The next one we'll dig into is kind of a heavily treed area here. You can see in the ortho photo, there is no ground visible through those trees in that particular area. And in both cases, again, we penetrated through the vegetation very well. You may see a few more ALS shots on the ground here, but what encourages me about the ULS data set, if I isolated it alone, I still would see my grade breaks in here. I wouldn't be missing anything necessarily from producing a topo of this particular area per se, even if my shots are just there's a fewer shots than the ALS data set. So again, driving towards that data equivalency from a quality standpoint. And then lastly, the land cover type where LIDAR always struggles, okay? The heavily vegetated, heavily low, thick vegetation, okay? And you'll see our ALS data set our ULS, excuse me, didn't penetrate this low vegetation in this right-hand screen capture nearly as well as the ALS did. My assumption is that the ALS data set truly got to ground here, but I don't know. That's why I've got my boots on the ground survey crew out there that's going to go out and shoot some check shots in these thick, low veg areas. Okay, the GPS quality is still going to be good if they're running topo through these, but those check shots are going to densify and confirm whether we either got to ground or we didn't get to ground, and add to our overall final design grade surface. Doesn't matter what system I'm going to use, I'm still going to shoot check shots in these areas. So I still feel comfortable flying the ULS data set, having that survey backbone out there. So I feel like we've reached an equivalency, based upon these screen captures, these cross sections throughout our project site, at least in our land cover types. Lastly, I'm going to touch on, these weren't part of the project necessarily, but we fly a lot of electric transmission and distribution work, developing PLS CAD models and final deliverables for our clients. So we wanted to make sure we achieve data equivalency again with our ULS and ALS system on these different types of features within our point clouds. And so we'll see here, you see here a distribution pole where we have plenty of hits on our wires, plenty of definition on the actual top of the distribution pole and the electric components up there. And we've got a little bit of the guy wire that's coming off the side there. And again, on the electric transmission side of things, not necessarily distribution in this case, there's plenty of data and an intermixing of the yellow being the ULS data, the red being the ALS data, an intermixing of getting plenty of shots on our shield wires, on our transmission wires, plenty of shots on our guy wires. We can see our connection points, see our insulators. Again, seeing that equivalency of data quality so that we can be. So I feel like we've reached a good equivalency from a quality standpoint. That again gives us the flexibility as consultants to put the platform and the sensor on the project that allows us to be most efficient from both a budget standpoint and from a schedule standpoint. And of course, the ALS is going to win from actual time on project from a schedule standpoint efficiency. But if I have to mobilize fewer people, fewer crews, fewer resources, or lower cost resources to the project, the ULS starts to catch up from a budgetary and a standpoint. But at the end of the day, we hit our quality metrics, okay? And that's what we're driving for, to deliver that good, high quality data to our clients and be good consultants. And so with that, I'll pass it back over to My-Linh. Thank you for your time, and I look forward to any questions you may have.
Excellent. Thank you so much, Matt. We have a few questions here. what was the speed and altitude of the Cessna dataset again, if you can share that?
Sure. I believe our altitude is about 2,700 feet and our speed around 130, 140 knots.
Excellent. And then another question is, did you have any independent QC points for comparison?
I did have some independent QC points in another project area, and you are correct, that would have bolstered this. I didn't have enough to have a relative sample size, a good solid sample size. I should go back and get some more. How's that? So.
Perfect. That actually transitions to another question. For the unmanned laser scanning system used, the Minivux 1 UAV is fixed at 100 kilohertz. How would you expect your UAV flight experience had you used a higher performance and longer ranging system like the VUX 1 LR, especially in the heavy and low vegetation areas?
Sure. And with the VUX LR, we're excited. We like that sensor because, again, it has a good range accuracy precision, similar to the Minivux, similar to the 1560 II. It allows us, though, to fly faster, fly higher, and get a higher point density. And it should give us a bit more vegetation penetration, being a higher powered laser in this case.
Everyone is asking questions right now. I'm just trying to read through them. How much time difference was there in between calibrating the two different data sets?
Time difference as far as acquiring the data sets or calibrating the data sets?
I believe in the calibration process.
Calibration process? It was calibrated about the same time, I would say. Or okay, are you talking time difference? I guess time difference from how long did it take to calibrate the data? Sorry, I'm answering a question with a question. It's not fair.
That is correct.
Okay, yeah. We've got a very stringent process that we put our data sets through at SAM, and we found that when we apply a very similar process to each one of our sensors, we get similar results, okay? So we put things through kind of our stock process and make small adjustments based upon the feedback that we get during that process, but it ends up being a very similar time to get the two data sets calibrated because of that standard procedure that we put them through.
So with regards to that, were you able to compare the accuracy of the data sets relative to each other prior to the addition of control points?
I did not do that comparison. I could have, yes, I could have done that comparison. And that can be very dependent upon the base stations that are utilized, the length of the baselines, the quality of the pod solutions up front. The UAS with the multiple missions, of course, tends to be a little noisier, a little more or a little different error models in between the missions, I guess you could say, versus the one mission from the ALS data set at that point. But what we do is run initial control reports all the way throughout our process. So we see as we apply a relative calibration to it, how it has affected the absolute calibration to the real world coordinates, even before we've introduced those into the calibration process. That lets us know if we have any outliers in our control reports or anything of that nature. So I do kind of have those comparisons that give me some indication. That would be interesting, though, to go back and run those DZ orthos, though. That was not done, I can tell you that, but that would be an interesting case study, too, to kind of dig a little deeper into it to see that.
Regarding the control that was laid out, how was that shot with? Was it with a GNSS receiver or a total station?
A GNSS receiver, using, in this case, So we always, set some primary control on the site. That primary control serves as the backbone of the site. And then, if we use VRS procedures, we're tying into that primary control point tied out to cores at that point, or we're using a single base observation or RTK observation off of that base station there. Just variable ways to get there, but redundant observations to give us a nice tight GPS survey that's very site specific.
Regarding your calibration workflow, what software do you make use of?
It's a combination of Rye Precision, Rye Process, and Terra Solid Terra Match.
Do you find many limitations on where you can use your ULS systems due to FAA restrictions?
We do. We fly, under Part 107, licensed remote airman certificate pilots, and then they go through, a SAM credentials, and I guess I'm digging a little deeper away from the regulatory, but just to kind of build to the experience level of our pilots. And then within the process of vetting a site for potential ULS acquisition, we're paying attention to airspace, TFRs, all of that good stuff. And I would say we typically say no more often to ULS acquisition than we say yes. But that's where achieving the data equivalency, we can say, okay, yep, this is a manned flight, this is an unmanned flight, and kind of going from there.
At what point does ALS become more cost-effective than ULS on a linear corridor project?
That's a good question, and that very much depends upon how often you want to be using your sensors to cover the costs, how efficiently you can fly corridors, how you design the acquisition plans. Yeah, I can't give you a mileage per se. I'm going to have to say it depends.
Sure, that makes sense. Okay, I think we have time for one more question. What is the visual line of sight range of your specific aircraft?
Sure. Our pilots, well, we're limited both by radio range and visual line of sight range. And unfortunately, our radio range with our specific aircraft, and that varies by site, and setup and whatnot. But we tend to stay within a radio range that is also a visual line of sight range. And I would say we stay really kind of within a mile maximum. We don't want to really branch out much more than that. And so our pilots are trained to and have a lot of experience in taking the designed flights and developing a home position that maximizes their visual range, and then making any adjustments that we need to, or having the office make adjustments to the flight plans to maximize their level of efficiency, both from a radio and a visual line of sight range, and a safety range too, of flying over things that we can only that we aren't not flying over things we aren't allowed to fly over. How's that?
That sounds good. All right, well, that's all the time we have for today. Thank you again, Matt, for joining us and sharing your experience using both RIEGL, ALS, and ULS systems, and for today's purpose, comparing their performance over the same site. If you have any additional questions regarding today's presentation, please feel free to contact Matt or myself directly at the email addresses listed here. Please stay tuned for October's webinar series schedule. Once it's made available, which I believe that email is being sent out tomorrow, you can find the registration links at the RIEGL newsroom, as well as on our LinkedIn page and all of our social media pages, or feel free to contact me directly. Thank you again, and until next time, have a good day. Bye.